Okay, so number 13. The charge entering the positive terminal of an element is this thing. The voltage across the element, plus to minus is... Okay, so what they're talking about is we've got something, and we're just saying this is the plus end, this is the minus end, and there's some amount of Q coming in, and the voltage, as measured from here to here, since it says plus to minus, what they say is it's the voltage at this point minus the voltage at this point. So it's the normal way of doing it. Basically what that means is that Q is, you just read it right off of there, 5 times sine of 4 pi t. Oh boy, millicoulombs. I hate it when they do that, like a function and then some units. It's so stupid. Voltage equals, I mean, there's no way around it, I guess, but I hate it. Voltage equals 3 cosine 4 pi t, and that is volts. See, the reason I hate it is because this unit is attached to the number that's outside of the sign. Because sine and cosine, they can't give you anything that has units. They don't return something with units. That means the 5 has units of millicoulombs. The 3 has units of volts. But what unit does t take? I don't know. It doesn't say. What units does 4 pi have attached to it? I don't know. It doesn't say. It should say where t is in seconds, where t is in milliseconds, where t is in microseconds. I have no idea. It doesn't say. So we'll just assume t is in seconds. Anyway. It's frustrating. Okay, anyway. What do you want me to do? So find the power delivered to the element at 0.3 seconds. Okay, fine. So power is current times voltage. Sorry, I got upset about that. It's just, they should specify, if they're going to say Q has this units, but give a function, they need to specify what unit every variable in there is in. Anyway, IV. So we don't have I, but we have V, so we need to find I. So we know that I is equal to dq by dt. So that means we'll not integrate it because we have q, we need I, therefore we'll do the derivative of that. And I'm gonna get rid of the problem statement for now, so just make sure you have that written out. So the derivative of that will be, I will have the 5, we're going to get a times 4 pi, and the derivative of sine is cosine 4 pi t. The units on that, since Q has units of millicoulombs, and we're going to assume that T has units of seconds, that gives us milliamps, because the milli is on top, the bottom has regular unit, therefore the milli transfers over, and we will get milliamps. V is just this. So now we plug it in. Oh, well, here, so this is going to be 20, right? 5 times 4 is 20, so we know that. So now we'll plug it in, and we'll have 20 times 3, which is 60, and we have the pi. And then the cosines have the same thing in them, so it'll be cosine squared 4 pi t, and the units will be milliamps times volts. Volts is the regular unit, milliamps is the prefix unit. They're multiplied, so it just carries over, and we'll get milliwatts. Yeah, we didn't miss anything, right? 20 and 3 is 60, pi, cosine, yeah. Okay, so then where'd it go? It's this one? Yeah. Power delivered to the element at 0.3 seconds. So we want t equals 0.3 seconds. Okay. So there they gave us a unit, but that doesn't tell us that t in here is definitely seconds. Anyway, it's okay. So T is 0.3, so we just need to get the calculator out for that one. All right, so we'll do cosine. Oh, also, I'm pretty sure they want radians, so just make sure you're in radians. Cosine, I based that on gut. There's no, I couldn't possibly defend it. Cosine of 4 pi times 0.3 is this. We want to square it. So square it, multiply it by pi, and 60. So 123.37. 123.37 milliwatts. So that is the power being shoved into that positive terminal at 0.3 seconds. Great. Okay. So part B, calculate the energy delivered to the element between 0 and 0.3 seconds. Okay, so we can do that. I'm gonna erase this. We don't need that value of power to do part B because that value of power is just for the specific point in time of 0.3 seconds. That's not really useful to us anymore. But what we do need is we need the energy. And remember that power is also the change in energy divided by the change in time. So if we want the energy, we want dW equals P dt. Integrate both sides. The left-hand side becomes the total change in energy. The right-hand side can become the integral from 0 to 0.6 of P dt. So this will be the total change in energy that takes place between 0 and 0.6 seconds. So we need to do the integral of this guy. So the integral of that will be, let's just do the sort of antiderivative, I guess, of it first. 60 pi cosine squared 4 pi t dt. Get rid of the question statement. So this will be 60 pi integral cosine squared 4 pi t dt. Now, I don't know what that is, but I think the textbook that I'm pulling these from has a section where they give you some integrals. Yeah, indefinite integrals. Let me see, can I share this? Yeah, there we go. So I'm just on the indefinite integrals. We're just looking for cosine squared. Okay, so cosine squared right here. So they have a, all right. So this will be 60 pi. Put the result in here. Our x is at t, so it's t by 2. Here, can I do this and then zoom in? Yeah, that's the one we're reading. So t by 2, and then plus sine of 2 times a. Our a is 4 pi. And t divided by 4 times 4 pi. And this is going to get evaluated from 0 to 0.6. Get rid of my head. There we go. So 60 pi. So that's going to be 0.6 by 2 plus sine of 2 times 4 pi times 0.6 divided by 16 pi. And then you would subtract the 0, but this term would become 0. Sine of 0 is 0, so we don't need to even mess with it. So what do we get? Calculator time. So we get, we'll just do this term first. We get sine of 2 times 4 pi, 0.6. Yep, divided by 16 pi. It's this plus 0.6 by 2. Okay, then times 60 times pi. 58.75. 58.75. And the units, so power was in milliwatts, and then we multiplied it by seconds. So we basically had dW equals P dt. I can't see that. I can almost see it. We basically had dW equals P dt. So P was in milliwatts. Time was in seconds. Therefore, this has to be in the milli version of energy. So that will be millijoules. So it's millijoules. There you go. All right. Bit longer than the other ones, and I think that we satisfied it, right? Let me see. Calculate the energy. Yeah, okay, cool. That's it.